circles? Well, hopefully you've heard of circles before. We're going to treat them in maybe a different way than you've seen before. So obviously you know that a circle is, the set of points which are a given distance from a certain point. I'm going to give you something that maybe you haven't seen before, which is an algebraic definition of a circle. That is, I'm going to define a circle using an equation. So a circle of radius r centered at hk, so that's the coordinates of the center of the circle. A circle of radius r centered at hk is the set of points xy satisfying the following equation. X minus h quantity squared plus y minus k quantity squared is equal to r squared. So that's the equation of a circle centered at h comma k and with radius r. All right. Let me just convince you really quickly that this is true. I guess you can sort of call it a proof. So let's suppose that here's a plane, like here's a grid, and maybe you've got your center right here, that's hk, and here is the circle. All right. Pick a point on the circle, say right here, and call it xy. My claim is that xy satisfies this equation right here. Okay, here's how you prove it. Well, for one thing, you know that this distance right here is r, because that's a radius of the circle. Now, what I want you to do is draw this right triangle, okay, like so. Now, just notice, what is the length of that side of the triangle? Well, it's the distance, it's basically the vertical distance between these 2 points, right? It's like the vertical change from here to here. So it's just the difference between the y coordinates. So it would be y minus k, right? This y coordinate minus that y coordinate will be the height of that triangle. Similarly, this side here, how long is that side of the triangle? It's just the differences. It's the difference in the x coordinates. So that would be x minus h, right? Now, hopefully you remember the Pythagorean theorem from whatever, 9th grade or something, which says that the length of this thing squared plus the length of that thing squared is equal to the length of that thing squared. A squared plus b squared equals c squared. So what does that really say? It says this, which is x minus h squared, plus this side squared, which is y minus k, is equal to this side squared, which is r squared. And that's exactly the equation I have here. Okay, so any point xy that you pick on the circle will satisfy this equation. So that's why this equation is, the equation of the circle. Okay. All right. So just a couple of examples. Suppose that I say graph the following equation: x minus 2 squared plus y minus 3 squared is equal to 16. In order to graph a circle, all you really need to do is find the center and find the radius. After that, it's easy. So what's the center of this thing? Well, if you compare this equation with the general form, you can see that h is 2, and you can see that k is 3. And the center of the circle is hk. So hk is going to be 2, 3. So that's where the center is. The radius, notice that this thing over here is r squared, so r must be 4. 16 is not r, right? The thing on the right-hand side of this equation is not r, but rather r squared. So this object here, the 16, that's r squared, not r. So the radius is 4. And then, you can obviously draw this, 2 over, 3 up. There's the center. Sorry. There's the center. And then you're just going to draw a circle of radius 4. You get it. All right, it's pretty easy. Okay, I'll make it just a little bit more interesting. Let's consider the equation graph x plus 4 quantity squared plus y squared is equal to 5. It's a little less obvious what things mean here. If you compare this to the general form of the circle, x minus h squared plus y minus k squared is equal to r squared. comparing these two structures, what do you think h is? H is actually going to be -4. So look, so what's the center of this thing? The center, as always, is located at h comma k. So what is h? H is actually -4. It's always the opposite of what it looks like. The explanation for that is this. H in the general form is the number which is being subtracted from the x. If you look at our equation here, what is being subtracted from the x? Well, not 4, because if 4 were being subtracted, it would say x minus 4. In order to view this as x minus something, you have to view it as x minus -4. So the h is -4. As far as k, if you compare these two expressions, you can see that k should be 0, right? If you replace k with 0, then you'll have y squared here, which is exactly what we have. So that's the center, and then the radius is, this thing here is, of course, r squared. So r squared is 5, meaning r must be the square root of 5. And if you want to graph this thing, I think actually, so the center's at -4, so I guess the center's right here. And then as far as the radius, if you really want to get accurate with the radius of root 5, ask your calculator. It'll be 2 point something, so a little bit more than 2, so something like that. Okay, that's pretty sloppy, but it's good enough. Okay, so now I want to talk about completing the square. Completing the square is a procedure for solving quadratic equations that you should have learned last year. So completing the square. And I'm just going to try and refresh your memory by solving a quadratic equation by completing the square. So let's consider the following equation, x squared plus 6x equals 2. So that's a quadratic equation. You could try to put everything on one side and factor it, but you won't be able to factor. I would use the quadratic formula if I were actually interested in solving this, but I want to review this procedure, completing the square. So how does that work? What you're going to do is you're going to add like a funny number right here to both sides of the equation. You're going to add some strange number to both sides. The number you're going to add to both sides is you look at the x coefficient, which in this case is 6. You cut it in half, and then you square it. So if you take 6, cut it in half, you get 3, and then square that, you get 9. So I'm going to add 9 to both sides of the equation. That's the funny number that I'm going to add. Now, why would you do that? Basically, this thing here is guaranteed to be it's guaranteed to factor in a very particular way. We need a pair of numbers that multiply to 9 and add up to 6. That's 3 and 3. So that's x plus 3 times x plus 3. The right-hand side, of course, is 11. Of course, x plus 3 times x plus 3 is better written as x plus 3 squared. And now the trick is that you can take the square root of both sides. If you take the square root of the left-hand side, you just have x plus 3. On the right-hand side, you have square root of 11. Don't forget your plus or minus. And then you can subtract 3 from both sides. So plus or minus root 11 minus 3. So that's completing the square. It's a method for solving quadratic equations. I am interested in completing the square because it is going to allow us to write equations of circles in the nice form that I just illustrated a moment ago. So back to circles. Let's consider the following. Put x squared plus y squared minus 6x plus 4y minus 12 equals 0 into center radius form. In other words, make this equation look like the equation for the circle that we just had a moment ago. Make the equation look like this. Now, right now, obviously, this equation doesn't look like this at all, but through completing the square, we're going to make this thing look like this, okay? The reason why we want to do that, basically, is that, if you want to know anything about this circle, you want to find the radius, you want to find the center, you really can't do that unless you put it in this form, right? So we're going to put this thing in this form by completing the square. So the first thing I'm going to do is I'm going to rearrange the terms so that the x terms are next to each other. So x squared and then minus 6x. I'll put the x terms next to each other, and I'll put the y terms next to each other, y squared plus 4y. And I think I'm going to bring the constant term over to the right-hand side, so adding 12 to both sides. Right? Okay, so now what I'm going to do is complete the square, but I'm going to have to do it twice, once for x and once for y. if you hide the y terms and just look at that first expression there, x squared minus 6x, it's very similar to the quadratic we just solved. I'm going to add a funny number right here, okay, to complete the square in x. And I'm also going to have to complete the square in y. I'm going to add a funny number right here. All right, so what is the number that I want to add here? You look at the x coefficient, which in this case is -6. You cut it in half, which gives you -3, and then you square that, which gives you 9. So I'm going to add a 9 right there. Okay? And then I'm going to complete the square in y as well. So I'm going to add a different funny number right here. What do I add? Well, I have to look at the linear coefficient, which is 4, cut that in half, I get 2, square the result, you get 4. So 4 is the number that I'm adding right there. Now, of course, I just added 9 and 4 to the left-hand side. Whatever you add to the left-hand side, you must also add to the right-hand side. So I'll also add 9 and 4 to the right-hand side. Now, why go through all this trouble? Because this expression here, the first 3 terms there, are guaranteed to factor in a very particular way. They're going to factor as x minus 3 times x minus 3. And then similarly, this term here, that expression is going to factor very nicely as y plus 2 times y plus 2. The fact that the two factors are the same, x minus 3, y plus 2, not an accident. The funny number that we add here is designed to produce that situation. Of course, on the right-hand side, we have 12 plus 9 is 21, plus 4 is 25. Now, obviously, x minus 3 times x minus 3 is better written as x minus 3 squared, and then same thing here. This is better written as y plus 2 squared. Now, all right, so we've completed the squaring both the x and the y, and wouldn't you know it, that equation looks an awful lot like this, right? This is the center radius form of the equation of the circle, and what we have looks very similar, right? You can see that h is 3 here, and k is -2, and r is 5, right? That's the radius squared. So this is a circle centered at 3, -2 with radius 5. But we had to put it in this form in order to see that. Okay, so just one more example, and then we'll be done. So I'm going to do one more example, but it's going to be a little bit painful. I just want to check on my time here. I know I've got a class coming up. I want to make sure I'm not late for it. Let's see, what is it, Wednesday, D block, starts at 2. Okay, we got all kinds of time. Okay, cool. So last example, and then we'll be done. So same instructions as the last time. I just want to put 2x squared 2x squared plus 2y squared minus 5x plus y equals 0 in circle radius form. So exactly the same thing that we just did, except a different equation. This one's going to turn out to be a lot more annoying, though, for various reasons. For one thing, all right, I guess I'll start in the same way as last time. Put all the x terms next to each other, put all the y terms next to each other. So, minus 5x, and then plus 2y squared, and then plus y equals 0. So here's the thing. In order to complete the square, the squared term must have a 1 in front of it as its coefficient. You can't have this 2. If you remember in the previous example, the x squared term was just x squared. It was like 1x squared, and same thing with the y squared term. You might remember this from last year. If you want to complete the square, you need to have a 1 in front of the squared term. You might wonder, how can you make that happen? You could divide everything by 2, and that would sort of nicely get rid of the 2's in front of the squared terms. I'm actually not going to do it that way, basically because that method will work for circles, but in the examples we're doing in the coming days, that procedure won't work. Here's a procedure which will always work. I'm actually going to pull out a 2 from these two terms here. Okay? If you pull 2 out of 2x squared, you're left with x squared. Now, if you pull 2 out of this term, it's not so obvious what you're left with because 2 doesn't go into 5. What you're left with is 5 halves x. If you don't believe me, just ask yourself, if you redistribute the 2 to these two terms, do you get back what you started with? Yeah, because 2 times 5 halves is just 5, right? Okay, so same thing over here. I'm going to pull the factor of 2 out of these two terms. So 2 quantity y squared plus 1/2 y. And again, if you don't believe me that that's what you get when you pull out a 2, just imagine redistributing the 2 and just notice that you get back where you started. Okay, so now that the squared terms have a 1 in front of them, this is like 1x squared, this is like 1y squared, we can complete the square. So we have to add a strange number, right? So we have to add a strange number right here, right? And what is that strange number? You take the x coefficient, you cut it in half, and then you square it. So the x coefficient is negative 5/2. Cut that in half, you get negative 5/4. Square that, you get 25/16. I'll say that again. Take this x coefficient, which is 5/2. Cut that in half, you have 5/4. Square it, you get 25/16. So that's the funny number that we add there. And then similarly, over here, we need to add a strange number right here. The strange number, once again, is you take the linear coefficient, cut it in half, and then square. So the linear coefficient is 1/2. Cut that in half, we have 1/4. Square that, you've got 1/16. Okay? Now, here's the thing. Whatever you add to the left-hand side, you must also add to the right-hand side. It is very tempting to think that we only added 25/16 and 1/16 to the left-hand side. But the thing is, this 25/16, because I've placed it within these parentheses, is actually getting multiplied by this 2. So what I really added to the left-hand side when I added the 25/16 is 2 times 25/16. So really here I added 50/16 to the left-hand side. And similarly, when I put a 1/16 here, because that 1/16 is getting hit by the 2, I didn't really add 1/16, I added twice that. In other words, 2/16. So in total, what did I add to the left-hand side? Well, this and this, right, which is 52/16. So 52/16 is what I added to the left-hand side, so I also have to add 52/16 to the right-hand side. Okay. Now, this thing and this thing are guaranteed to factor in a very nice way. How do they factor? Well, you need a pair of numbers that multiply to this and add up to this. Not so obvious when you've got fractions. However, remember that I said that these things are guaranteed to factor in a very particular way. Namely, the two factors will be the same. It'll be like the same number twice over, like 3 and 3, or 5 and 5. That's really telling you that this thing here has to be the square of the number, up to a minus sign. If you think about it, it's going to be x minus 5/4 quantity squared. If you FOIL this out, right, you're going to get this, negative 5/4 plus negative 5/4 is this guy, negative 5/4 times negative 5/4 is that guy. Plus 2. Same thing over here. I need a pair of numbers that multiply to 1/16 and add up to 1/2. That's going to be 1/4 and 1/4. Right? 1/4 plus 1/4 is a half. 1/4 times 1/4 is 1/16. Over here, 52/16, that can be reduced. I guess it's like 26/8. I guess we can reduce that even further. Whatever, I'll do more in the next step. So finally, this is almost in the desired circle radius form. The only issue is that we've got these 2's in front of the parenthesis terms, which are not supposed to be there. If you compare that with the general circle radius form, it doesn't look like that. So one way of getting rid of these 2's is to just divide everything in the equation by 2. So if I divide everything by 2, then I get the following. Dividing this guy by 2, you just divide the numerator.